So if things look a little weird, it's because I forgot to share my screen. So I start this over again. It's okay. Only got like 10 minutes. It was fine. So here's the deal. Finish doing more follow-up things. Is it better to study end of chapter problems or tests from last year? What I recommend you guys do with the test from last year is to set a timer for 80 minutes and take it like an exam, because then you can kind of get an assessment of how you're doing. So this does, when I say take it like an exam, I do mean give yourself that potentially useful information page so that you have it. Use the same calculator. If you can, be in a quiet place, and 80 minutes and just see how far you get. Then that way, if you figure out like, oh man, I need some more work with kinetics, you can go to the end of chapter problems and hit chapter 14 up. If you need help with osmotic pressure, end of chapter problems. Especially as we get closer to the exam, having an idea of what you need to study and what is more valuable is helpful. So using the old exam to basically kind of assess where you're at can be really useful. Because otherwise, as far as like which one's better, both of them, especially because for at least some of my questions, I used the end of chapter problems. I actually like looked at like what was assigned and grabbed a lot of that language. I couldn't always use exactly the same problem, but I actually did look at your end of chapter problems to write some of my exam questions this year because I forgot when they were due. Sorry, I thought they were due on Saturday. They were due on Friday. So I had to hurry. So I looked at the end of chapter problems. Which formula is in Kelvin and which is in Celsius? So if we take a look at the potentially useful information page, what you'll find is there are equations, and the equations will actually tell you. So here I have things that have a big capital T for temperature and a KF. And if I go to my table where I have KF, it actually shows that that's in Celsius. So you can actually look at that potentially useful information page to tell you which one's in Kelvin and which one's in Celsius. Your change in temperature is in Celsius. Your temperature, that's just plain temperature for osmotic pressure, has the gas constant, and the gas constant is in Kelvin. So another way to think about this is when we are dealing with an absolute temperature and you're just going to plug temperature into the equation and multiply it by something, that's when you need Kelvin. When you've got temperature, but you're going to add or subtract it, and that's what happens in boiling point and freezing point calculations, you can use Celsius and it's just fine. So this does have a lot to do with the mathematical operations that you're going to use. So you can either take a look at the potentially useful information, take a look at the units, and the units will tell you, or essentially, if you can multiply by temperature, you're going to use Kelvin. If you are going to add or subtract, you can use Celsius. So hopefully that helps. So, okay, I did this one, this one. This one is a little bit small. Sorry about that. I didn't bump them all up. But it asks something like, well, we have to calculate the experimental Van Hoff factor. You certainly can. It's definitely fair game on the exam. So I won't flash back to it, but we had equations that looked like this. Oh, I'll put it in the right spot. And so essentially, while usually we use these to calculate the new boiling point or calculate the change in boiling point, if we gave you a new boiling point and the molality, you could solve for the Van Hoff factor. You could solve for that I. If we gave you enough information about osmotic pressure, then again, you could solve for the Van Hoff factor. So you've got two different equations that have the Van Hoff factor as part of them. That, again, as long as you had enough information, we could certainly ask you to solve for the experimental Van Hoff factor. Absolutely. This question was one that did get asked basically like almost a week ago, as I'm making this video. So can you please explain the integrated rate law and will it come on the exam? So we'll be on the exam, yes. I'm going to do a brief explanation, just because I think by now, hopefully y'all have seen more of this in class. We'll go ahead and use this to chit chat a little bit. So first of all, when it comes to integrated rate laws, there are a few of them, but one thing to keep in mind, hey now, one thing to keep in mind when we are talking about rate laws and integrated rate laws is that since I have different rate laws, so my rate could be equal to K times the concentration of A, but another rate law could be rate is equal to K. We'll use a different, we'll say B squared, right? So this is a second order overall reaction. This one down here is a first order based on the exponent that's here. So in the case of the A, there's no exponent visible, but that means it's understood to be 1. In the case of the other one, it's squared, so it's a second order rate. When I then look at this with a natural log is first order, and that is information you need to have in your brain by yourself. We will not label that for you. The fact that the natural log gives you a first order, the natural log is the equation you need for a first order reaction. In here then, this is what I referred to as a natural log. So natural log is what that is called. On your calculator, it might be lowercase like this, or it might be uppercase like that. I don't know. Everybody's got different calculators, and that's all okay, but that also means I don't know exactly where that button is or what it looks like. But some things that this then has, so since the goal of identifying the rate law is to have an idea of how the change in concentration affects the rate. When we talk about things that can affect kinetics, remember that concentration matters. When you have more reactants better able to bump into each other, just having more reactants all smushed together, they're better able to react. So you usually have faster kinetics when those particles can find each other more easily. So a higher concentration means a faster rate. When you look at this graph here on the left, that's part of what they're actually showing you is when my concentration is high, I actually have a pretty fast rate. I was trying to draw a straight line on this graph and it failed miserably. So if this is my point on my graph and I could try to draw a straight line through it, how fast my reaction is going at that concentration is pretty fast. Whereas when we look at way down here, it's going a lot slower because the concentration is lower. So as the concentration goes down, the reaction starts to slow down, or the reaction goes slower. So therefore, we want an equation that will tell us information about that. So if we have an initial concentration of 1 molar or initial concentration of 0.02 molar, we want to know what is that going to do to the amount of time, how fast will it go, how long will it take for it to get to a certain point, or will I still have stuff that I can visibly measure after a certain amount of time has passed. So that's why we have this, which with this little 0 here, this is the initial concentration. This is just supposed to be, there's supposed to be a little t there. This is the concentration at a time. And whatever that time is also right here. So if I want to talk about how much is left after 2 minutes, how much is left after 3 hours, how much is left after 5 seconds, I can do any of those things with that equation because I have the time factor in there. And then here is my rate constant. So one of the few things that does in fact just carry over from our rate law is our rate constant. Same exact rate constant that we had before. So all of those components do go into that equation. We get to use it as is. When we take a look at our potentially useful information sheet, you'll actually find a couple of different ones over here. I actually labeled some of these. So these two are both first order. This one down here is second order. This one that I have the line through is 0 order. I put the line through it because we won't ask you questions to solve a 0 order reaction, but we can still You either use zero order options as wrong answers is an option, or somehow discuss zero order reactions, usually in a way that would be the wrong answer, but it is not, it's on there. So it is sometimes useful to know what that thing is, which is a zero order integrated rate law. The thing below it that also says first order is a half-life, by the way, that's what that is. So I didn't explain everything about integrated rate laws, because that usually takes about 2 class periods. But at least hopefully that gets you started in thinking about what integrated rate laws are, and what components of those equations there are. Like anything else, we can ask you basically any question for any of these. So we could ask you about the amount of time, we could ask you about the new concentration, we could actually ask you, like, if you have this much left, how much was there originally? We could have you solve for the original concentration. Any of those will work. We're going to actually answer this one down here. Will colloids be on the exam? No. No colloid. How does the temperature affect solubility, depending on whether the reaction is endothermic or exothermic? So the short answer to this one is, if my delta H of solution is endothermic, then adding heat or increasing the temperature will increase the solubility. So if I have a reaction where my heat of solution is endothermic, it requires energy to get it to go into solution. If I add more heat, that becomes more soluble. A physical example of this is something like sugar in water, where when you try to get sugar to dissolve in water, it does dissolve, but if you heat that up, it'll dissolve much faster. And you can get more of it to dissolve as well. So if the overall heat of solution is endothermic, adding heat will increase the solubility. If we're talking about a delta H of solution that is exothermic, then adding heat, that is increasing the temperature, will decrease solubility. Solubility. So the hard thing is that an exothermic reaction, we just don't see as much. I was in class using an example of gases dissolving in liquids, because gases dissolving in liquids is always exothermic. And so when you talk about decreasing solubility, that means that the gases that used to just all be in the liquid and dissolved are not going to be dissolved anymore. They're going to form bubbles and come out of the solution as a gas if you add heat to this. And maybe the best example of this is, you might not have ever done it because you might have been warned against it, or maybe you have not spent an entire summer down here in Texas. But in Texas, you do not leave a can of soda in a car in Texas in the summer outside, because the temperature inside the car will get very, very hot. And it gets so hot that the solubility of those gases goes down, which means the gas comes out of solution as bubbles, and that can of soda will explode. And then you have soda on the inside of your car. And that's not good. Often it's sticky, or at least wet. So those are both things that happen. Now, one of the reasons why I think people often come back to these two ideas is because when I do it in these terms, endothermic, add heat, more soluble. Exothermic, add heat, less soluble. Everybody's usually okay. The hard thing is, We could also talk about each one of these if you made them colder, which means the opposite things happen. So not only do we have right now a pair of opposites, endothermic versus exothermic, add heat to either one of them and the opposite thing happens. But then I could also talk about, instead of adding heat, I could talk about making the solution colder or putting the solution on ice. And then the opposite things happen. So anytime things go in pairs, anytime you have opposite things happening, this is sometimes more difficult for your brain to hang on to because there's a lot of, well, is it this way or is it the opposite way? So this is a good thing to study, a good thing to look back on. I didn't go all the way back to thinking about equilibrium and Le Chatelier's principle. So I'm trying to give a short version of this because no one needs to look at this but me, but I am keeping an eye on the clock and I have to open my door for office hours at 2. One of these is, how does multiplying mole fraction with the pressure of a solvent give me the pressure of the solution? I actually like this one because I'm going to grab the chart, the picture that I didn't have to make. That came out of a textbook, or I stole it from Dr. Diekman so long ago. I don't even know where this came from, but it's great. It's a great picture. So here's the deal. We are going to have to make some stuff up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Seriously? So anyway, there's not a nice even number, which makes me a little mad. So here's the deal. Here is my solvent. It has a vapor pressure. We're going to say that this has a vapor pressure of 100, just because it's a nice even number. 100 torr. Why not? This is a solution. What has happened in the solution is there are physical solutes that are now blocking access to the surface. So if we're going to just take a little guess at this, and we're just going to go ahead and say that the mole fraction of the solute is 0.5. There's a lot of solute in here. I'm going to say it's about half. I did not actually count all these circles, so you can definitely argue with me that it is not half, that it's a little less than half or a little more than half, and I would believe you. But I'm just going to assume that it's about half. Looks like a lot of red dots. I should count them. I am not counting them. So because about half of this now is solute, I should basically expect about half of this to be solute, except that the solute's not actually able to go into the vapor phase. So I don't get half of it into the vapor phase. So since I don't get half of it in the vapor phase, I just only have half. So to put that in some mathematical terms, the vapor pressure of the solution is equal to the mole fraction of whatever is left. So this should be the mole fraction of the solvent. So granted, in this case, 1 minus the mole fraction of the solute is just 0.5. So maybe I should change this just a little bit. Let's make the solute 0.45. And now I can have my solvent be 0.55. That way it's a little less than half. So because basically I'm trying to report on what is in the vapor phase, not what's missing, but what is in the vapor phase. So I'm trying to talk about these dots and what dots I actually have left. So that's going to be the mole fraction of the solvent, the thing that's left, times the vapor pressure of the original solvent. So that actually is where that equation comes from, is by just trying to say, so what's left? I can't talk about the solute because if I have a non-volatile solute, there's no vapor pressure from that. But I can talk about how much of my solvent is still there. That is why that is mole fraction. Can I just go over all the equations of chapter 13 and 14 and when to use them? go over some of them. I'm going to have some problems at some point, but we'll see how I do. And part of the reason why I said I'll try is some of these things we can talk about that we're not going to use yet. So the calorie, we'll use it later, but we're not going to use the calorie right now. We're not going to use the Newton right now. That's also later. We're not going to use this stuff right now. That's later. The gas constant, changing between Celsius and Kelvin, changing between different units of atmosphere. These are all conversion units that can be helpful. This table can be useful. The hard thing with this stuff is looking at all the different types of units we have for concentration. Some of these we will need because we'll just ask you point blank, I have a certain molarity of solution. Tell me about the molality of the solution. Other times we'll give you information about the solution and say, tell me about the boiling point. And if I ask you about the boiling point, then you might be down here and being like, well, now I need an equation that has boiling point in it. That's this thing. That's one of these guys in this little row column thing here, boiling point. But it's got a little lowercase m. What was lowercase m again? Lowercase m is over here, and it's the moles of solute divided by kilograms of solvent. So I understand the idea of like, can you just tell me what everything is? And the difficult thing is some of these go together in interesting ways. This is vapor pressure lowering. That's what that one is. These two that I've scribbled on a little bit are osmotic pressure. Osmotic pressure. This is freezing point. This is dealing with stoichiometry of a solution. So in this little box here, this is kinetics with stoichiometry. Over here in the box, we've got first order integrated rate law, second order, zero order, and then a first order half-life equation. And then I always have to look up which one of these is which. You would thought I would have gotten it by now. So honestly, I have two different strategies that I usually use for half-lives of higher order kinetics. And one of those is to look at it right beforehand so I don't mess up which one's which. This is second order, this is zero order for half-lives, but we're actually only going to ask you guys questions about first order half-lives. So you actually don't need these either. There's some other notes on here about other things that will be coming up soon, but not on this first exam. So I know that that's not really enough to walk you through how to use all of those, but the difficult thing is kind of as pointed out earlier, since even just thinking about boiling point, that's got a change in boiling point, a Van Hoff factor, a molality, actually, and a constant. That's 4 different things. And as long as you had enough information to have 3 out of those 4 things, you could then have 4 different kinds of calculations just for that one equation. So as far as how to use them, I have personal struggles with that just because if I told you that it was a non-dissociating solute, so it's an I of 1, and 1 molal, and here was my original boiling point, and here's my new boiling point, so you could calculate the change, you could tell me what the constant was. So how to use each one of these. The main thing I would actually just say is if you haven't looked at natural log on your calculator, do also realize that in order to get out of the natural log, so if I have the natural log of this concentration is equal to negative 0.1, in order to actually get to that concentration, I do have to know how to undo the natural log, which is raising everything in an exponent with e. So usually e and the natural log are close to each other on your calculator. They're usually the same button. But that would be the other thing to have some background in, is how to undo the natural log. Okay. So one of these is a particular question out of the workshop. Let me see how much time I actually have left. This one says, are colligative properties part of the things that affect solubility? No, so colligative properties are basically looking at what happens to the solution once things are dissolved in it. So we don't actually say that colligative properties, that we don't say that vapor pressure affects solubility. Instead, we look at what the new solution's effect is on the vapor pressure. So they go in the same chapter because they're both about solutions, but basically kind of the beginning of chapter 13 is about how to describe solutions and what things can influence what happens when something does dissolve. And then the back half in colligative properties is cool. Now that you have a solution, how is that different from what you started with the pure solvent? So it's kind of in two pieces. I got a lot of like how to tell if a molecule dissociates. So I think I covered some of that with the original review, but I'll talk a little bit more about this idea that that there's two main things that we're going to look for. One of them is the notion of an ionic compound. So all of these lovely light green things are metals. These blue things, including hydrogen, are nonmetals. So if you have a metal plus a nonmetal, you can talk about that dissociating. So a metal plus a nonmetal will have some sort of I value greater than 1, because we're going to expect that to dissolve or separate into pieces. So if I have something like magnesium chloride, that's going to give me 1 magnesium into chloride pieces, which would be an I of 3. Some other components that you do need to know in there to help you out is you do need to know your strong acids. And you do also need to know your, give me a minute, strong acid nomenclature. I was like, it was something that made a lot of sense. Nomenclature. So strong acids, there are 7 of them. They are these 3. That is hydrochloric acid, hydrobromic acid, hydroiodic acid. And then there is nitric acid, HNO3. There is sulfuric acid, H2SO4. There is chloric acid, HClO3, and there is perchloric acid, HClO4. So those are the seven strong acids for y'all to know and remember back from Gen Chem 1. So you should know your 7 strong acids for this. The nice thing with the Van Hoff factor in your strong bases is that your strong bases actually fall under ionic compounds. So we could certainly need you guys to know that sodium hydroxide, you're going to get a sodium ion and a hydroxide ion. But this one, you're actually going to know because you're going to remember the hydroxide ion as a polyatomic ion, and then the sodium is a metal. So strong acids, yes. Strong bases, technically, those are ionic compounds. So not so bad. Why is it when boiling point increases, the freezing point decreases when a non-volatile solute is added to it? This one I actually did in the previous follow-up video, where I was trying to talk about the difference between boiling point and freezing point, and boiling point dealing with vapor pressure, and freezing point dealing with physical items basically being in the way of freezing happening. So those are just 2 different aspects of what's going on in there. So I did talk about the graph in the previous video. Then one's identifying exothermic and endothermic reactions. There is hanging out in the notes a slide that just has that on it. How to know if something is endothermic or exothermic and different terminology that we might potentially use. Where is it? Come on, I know it's in here. I made the slide, I promise. There it is. So these are some of the ways you guys can pause a video if you'd like to know if something's endothermic or exothermic. So there is basically a list of just how to know when one is one and when one's the other. So, oh no, got all these words on top of each other. So one of the things that I'm going to recommend in general, because I'm going to run out of steam to keep going. Oh, there's endothermic and exothermic. I guess I did in the last video. This idea that apparently I've already done some things, but I just can't remember, is honestly the reason why I'm just going to go ahead and stop for right now. I do apologize if I didn't answer your question. I really like answering questions, and I know that I just did not get to all of them. I do have office hours. You guys can't always email me. Ironically, that's what I'm going to do when I get off of this, is answer some emails that I've left alone. Do make sure you guys are going to take a look at the old exams that are posted in e-learning. Because sometimes people will be like, well, I was going to look at that, but one of the things that I personally think is really helpful about looking at last year's exam is this is the place, the time where the questions are in a random order. Pretty much all the other places where y'all look at exam questions or look at potential practice questions, they almost always have a heading that tells you what this is. So I do recommend that you guys take a look at the old exam so that you guys can just see, what is this? Is this from chapter 13 or chapter 14? Is that a colligative property? Is that solubility? Like, what is happening? What do the formats look like? What's going on? So do take some time to look at this, because in ALEX and even the end of chapter problems, there's basically labels to tell you what things belong in what section and can help remind you. But that's not what the exam looks like. The exam, they're all in a completely random order. They're actually put together with a random number generator, believe it or not. So not only are they random, they're really random. Random number generator, random. But again, hopefully some of this has been helpful to kind of think about and think through. Good luck. You guys can do it. Don't forget to practice with the calculator you're going to practice with on the exam. Bye.